So today I want to take a closer look at these two terms, reflection and scattering. I need to make sure that everyone is on the same page regarding these terms because the terms define the language. If you are not on the same page with the terms, then there are going to be misunderstandings, and misunderstandings often lead to bad feelings. So, everyone thinks they know what reflection is and what scattering is, but do we all think the same thing? That is the question. And as I have been saying over and over again in my video series, the problem is very often with the language. So when people have misunderstandings, and often when people argue, the problem is not with anything other than the language, and so they're using the same words or they're using different words and they have different meaning, and so the problem is with the language because the language has ambiguity. Okay, and ambiguity leads to confusion, and when people are confused, guess what? They get mad. When people are confused, they they lash out and they don't behave properly. And so the what I want to do, okay, what I plan on doing and what I'm trying to do and what I have always been trying to do is remove the ambiguity from the language. Okay, so I want to rewrite the program. I want to clean up the code. And then I want to re-explain everything using only the unambiguous terms. And so we can remove the ambiguity. If we remove the ambiguity, we are going to remove the confusion. Okay, so that is, basically that's my thinking. That's the way I operate, and that's the way I think. And so, I'm a computer programmer, so I'm always thinking in terms of what do I do when I rewrite a program? I want to clean up the code. I want variable names that make sense. I want other people to be able to read my code and understand what I'm doing. And so, so that's kind of how I approach the language of theoretical physics. And I want to remove the ambiguity from the language. So that is what I'm going to try and do in this video. And so this video was originally called Demystifying Reflection and Scattering, and that is mostly what this is going to be about. But before I do that, I just want to show you my latest approach to the ferro lens. The previous ferrocells usually had lights coming from the outside, pointing in towards the glass on the edge, and so when you do that, the light is the light source is not in the ferrocell, but it's actually behind the ferrocell, and that creates some issues. And so I decided that I'm going to remake a light box such that you can see the whole of the LED. So I think I showed you this in my community section. So here is an LED, and you can see clearly that the main light source is in the very middle of the LED. And so this is the light line, curved line that that AB's simulation is trying to replicate. Now you can see there's also some reflection here that creates a light source. It's a more diffuse light source, and so it doesn't extend very far, but you can see it's also doing this curved shape, and you've got another reflection out this way causing another light curve out here, but it's not enough to go all the way around. And so the only one that goes all the way around is the one from the original light source right in the middle of the light here. And so I want to build a light box where I can see the whole LED and I can see this whole line, because I don't want to so with this one here, the light source is out here somewhere. It's not actually here, but it's out here somewhere. And so you've got the light curve going on the outside. So the curve gets cut off a little bit, when the LED is on the outside of the Ferrocell, but so I want to build a light box where I can see the whole LED and I can see this whole circle, and then I will get this configure the simulation to create this curve so where I can see the whole curve. Okay, so that's why I'm doing this, and you know, here is just a little schematic of that. The idea is that I want the LED to be under the Ferrocell instead of over here. Okay, so my previous light boxes have had the LEDs coming from the side, where you could have the light sort of like that, but I want the light to be here so I can see the whole light curve that's being generated by the light source reflecting off the nanoparticles. So in the process of disambiguating the terms, reflection and scattering, I think the best place to start is with the definitions themselves. And so the definition of reflection is, reflection is the change in direction of a wave front at the interface between two different media, so that the wave front returns into the medium from which it originated. Common examples include reflection of light, sound, and water waves. Okay, so all waves have a phenomenon called reflection. The law of reflection says that for specular reflection, the angle at which the wave is incident on the surface equals the angle at which it is reflected. Mirrors exhibit specular reflection. So specular reflection is, perfect reflection. Okay, specular reflection is the law. Okay, so angle I equals angle R is the law in the ideal reflection circumstance. Okay, so that is reflection. Okay, so reflection is the incident ray. Okay, the angle, so you have an incident ray coming in, it reflects in a direction such that the normal to the surface, which is the orthogonal, the perpendicular, so the line perpendicular to the surface, the angle on either side would be the same. So the angle of incidence, this angle here, is equal to the angle of reflection, this angle here. So that is the law of specular reflection. Okay, so that is not ambiguous. This is not ambiguous. This is a term that I would choose and a definition that I would choose for my language. But here is where the misconception comes in. Okay, so someone recently said this to me. They said, reflection is what flat surfaces do. And so is this true? Okay, reflection is what flat surfaces do, true or false. Now, when they depict reflection in a graph like this, in a schematic like this, they often have a flat line here and an incident ray coming in and a reflected ray going out. And so you would think that you need a flat surface in order for reflection to take place. But here's the thing. What about curved mirrors? Okay, curved mirrors are not flat surfaces. Curved mirrors are, in telescopes. In telescopes you have curved mirrors, and those mirrors are very, very refined mirrors such that the reflections that happen off the mirror can be perfectly predicted. So the idea is specular reflection is reflection that can be predicted by the ideal. If you know the curvature of this curve and you know where the incident light hits, you can predict the reflected light. And so this is clearly not true. Reflection is what flat surfaces do, because curved surfaces can reflect as well. And of course the ferrofluid itself, here's ferrofluid near a magnet and, you know, there's a lot of curved surfaces, and I see a lot of reflected light going on here. So I would have to say false to reflection is what flat surfaces do. So the point of this is to show how, you know, a picture like this might lead someone to believe that reflection is what happens off of flat surfaces. Yes, you do need to know the normal to a surface, and for that you need to maybe even pretend that there's a tiny little flat surface there. But you know, basically, I know people think, okay, you have a mirror, only a flat mirror will reproduce the exact picture that is reflecting off of it. And yes, so there you need a flat surface for a mirror, but reflection does not require a flat surface. So Tim Vanderelli thinks that my use of reflect is incorrect in my language regarding the ferrocell. And he also thinks that I don't understand what scattering means. And so I think, you know, whenever and I'm going to tell you right now that I believe that the term scattering is an ambiguous term. And I think it's actually used incorrectly in general. And so let's just go to the definition of the term scattering, okay? Scattering is a term used in physics to describe a wide range of physical processes, okay, where moving particles or radiation of some form, such as light, sound, light or sound, like ultrasound possibly, are forced to deviate from a straight trajectory by a localized non-uniformities. Okay, this includes particles and radiation, so this happens in both, in the medium through which they pass. So let me read that again. Scattering is a term used in physics to describe a wide range of physical processes where radiation of some form is forced to deviate from a straight trajectory in the medium through which they pass. Okay, so this also includes deviation of reflected radiation, and this is what we're talking about here in the ferrocell. So this also includes deviation of reflected radiation from the angle predicted by the law of reflection. Okay, so the key words here are scattering is a deviation from prediction. Okay, so scattering is a deviation from prediction. Okay, so scattering comes after the prediction. You need to have the prediction before you can have a deviation of the prediction. So this is where I think the misunderstanding of the word scattering arises. Okay, scattering isn't the reflection. Scattering is the deviation from the predicted reflection. Okay, so reflections of radiation that undergo scattering are often called diffuse reflections. Okay, diffuse reflection. So this is the term I would prefer to use because it's very clear that reflection is an important part of diffuse reflection. Okay, so and then unscattered reflections are specular reflection. So perfect reflection. So you have to start. Okay, so here's diffuse reflection. So here's the incident ray, and here's the specular reflection, the ideal predicted path, and scattering is the deviation from the predicted path. Okay, scattering is a deviation from the predicted path. Okay, diffuse reflection is reflection with scattering. Or you could equally say reflection with deviations. Okay, so I could remove the term scattering from the language. Okay, because it's used very loosely. People use it loosely. Oh, scattering. People are scattering. They use it very loosely when scattering is really the deviation from the predicted path. So you have to have the predicted path. Okay, so as a computer scientist, I cannot implement scattering without knowing what the ideal path was in the first place. I need to know the ideal path, the predicted path of the light in order to implement something called scattering if I'm going to simulate what I'm trying to do, what AB and I are trying to do with the Ferrocell. And so you need the predicted path first, then you can implement scattering. Okay, scattering is the deviation from the predicted path. And, so this is where the confusion comes in because, people write the word scattering in papers, and just because someone writes the word scattering in a paper and use it to mean diffuse reflection is really what they're talking about. This would be a more accurate term here. Okay, diffuse reflection is, you have to have reflection first, of course, to have diffuse reflection. And so it's scattering with reflection or scattering with deviations. And so if I were going to define my own language, I would ditch this word and replace this word with diffuse reflection when talking about reflections. Okay, there's other kinds of scattering. Okay, scattering is a term used in physics to describe a wide range of physical processes of radiation that are forced to deviate from a straight trajectory. So straight trajectory is, one way. Scattering can be a deviation from a straight trajectory or reflected. And so for the Ferrocell, we're only really concerned with the reflected trajectories. So I would actually prefer to ditch the whole term scattering and opt for the term diffuse reflection. Okay, so I would use diffuse reflection, and if I use the word scattering, they are not equal. Okay, I can't write. Anyways, diffuse reflection is not scattering. Scattering is only one aspect of diffuse reflection because you need to know the ideal path before you can calculate before you could, create in a simulation the deviation from the ideal path. So I hope that's clear. I think this is a very important point, and people say scattering, but they really mean diffuse reflection. So that is demystifying the terms. Go back to the beginning here. Okay, demystifying language in terms of reflection and scattering. So here are my unambiguous definitions for these terms. I define reflection as the predicted path. I define scattering as the deviation from the predicted path. Okay, and diffuse reflection is reflection with scattering. So it is reflection with deviations from the original ideal or predicted path. So I think that's really straightforward. I think if we agreed to use these terms, that there would be very little confusion in our conversations with each other. I think we would be more clear about what we're talking about, especially in terms of the Ferro. And there's one more thing I want to point out regarding scattering. Okay, so scattering is a deviation from predicted path. Okay, when you look at the curved mirrors, okay, I want to make this point that this is not scattering. Okay, so when you have a reflector, when you have a mirror, which is a really good reflector, the path that the light takes is a completely predictable path. It is not, there is, very little deviation. Let's just say not zero, but a very little deviation from predicted path. And so the light that reflects in different directions, like in this one, the convex mirror, this is not scattering. So just because the arrows go in many directions doesn't mean it's scattering. Okay, scattering is a loss of information. Okay, reflection is information. So in terms of information, you can think of it this way. The incident light is information. If the reflection is perfect, then you've retained the information. So you can predict, you can, go back and figure out where that light came from. But if you have scattering, you've got scattering is a deviation from predicted path. So scattering, because it's a deviation from predicted path, you can't tell, say, from a scattered arrow where the information came from. So reflection is information and scattering is loss of information. So in a way, reflection and scattering are incommensurate principles. And the interesting thing is that in most images, especially, in the Ferrocell, is made of information plus loss of information, because there is going to be some imperfections in the Ferrocell that are going to create some scattering. But scattering is not the information. Okay, scattering is not the information. These lines are information, and the imperfections in the lines, like the thickness, the fuzziness of the line, okay, that is scattering. That is loss of information. Okay, so when you see something fuzzy, and actually these lines in the Ferrocell, at least in this image I took here, the lines are very thin. There is very little scattering going on in this Ferrocell. These lines are quite amazing, actually, in my opinion. There is very little scattering going on. So the reflections cause the lines, the scattering causes the slight fuzziness of the lines, and but the path that the light takes is completely predicted by the law of reflection off of a curved surface, which the nano cylinders would be. So they would be more like this. They would be more like this under the hood. And as you can see from the simulation, we have incorporated a kind of diffused reflection. The edges are fuzzy, as they are in the Ferrocell. And so yes, our simulation is a little bit more contrived than the actual Ferrocell, because the Ferrocell is underneath glass, and it makes the image look a little blurry. But regarding the thickness of the lines and the location of the lines, and the paths of the lines, you can see that the simulation is quite good. And there are other features of this that are inherent in the algorithm, and so we will get to that next. So Tim Banderelli told me that I'm taking the easy path and created a simple geometric 2D wireframe model. Okay, so this is not a wireframe model, even though it looks like it might be wires, but it is no more a wireframe model than the actual Ferrocell is a wireframe model. Okay, this is a simulation. It is a, you might want to think of it in terms of a probability distribution. Okay, so when you see the yellow line here, this is, the line that has a probability of finding a yellow reflection along that line. And so the green line is, probability of finding a green reflection along that line, given the, the magnet and the orientation and positions of the lights. And so, definitely, this is not a wireframe model. It is a computer simulation. I'm not saying, the software is not saying, oh, draw a line here and draw a line here and draw a line here. It is, predicting where a human being or a camera will see a light given the position of the observer. So in this image here, the observer is you looking towards the screen in both of these images. And so the lines are predictions. These are predictions that the software makes as to where you will find these lines in the actual Ferrocell. And so no, this is not a wireframe model by any stretch of the imagination. It is a picture. It is a projection in the same fashion that this is a projection, because the camera is above the ferro lens, and the camera receives the light from the ferro lens and takes the picture. And so this is simulating exactly what is going on here from the perspective of the camera. This is what the camera sees. This is what the camera sees. Okay, this is not what's inside the Ferrocell. This pattern is not inside the Ferrocell. This pattern is what gets reflected to your eye, what gets reflected to the camera. Okay, so that is why we have to input the camera position into the simulation. It is very important to know where the camera is in the simulation, because the simulation is predicting where the light is going to go from the light source, reflecting off the nano needles and into your eye. Okay, so that's how the Ferrocell is working, and that is how our simulation, this is what our simulation is simulating. So Tim also complained about the color source lights don't match up with the same colored curves in your sim. Okay, so the reason for that had to do with what I was talking about up here, and how the light source was outside of the simulation. So some simulations I was doing, the light source was outside of the simulated ferro lens. And so that's one of the reasons. The other reason is that there was a bug in the program that was not placing the lights in the correct location for another reason, and that is now fixed. And so now you can see that the light goes right through the light source in this simulation here. So Tim also said that he wants to hear my explanation of why we produce a new color when two different colored paths intersect in 3D space. Where is that shown in your simulation? Okay, so first of all, this is not happening in 3D space. This is happening in your eye or in the camera. But he wants to know why you get two new colors when the paths intersect, and where is this shown in the Sims. So I'm going to show you where it is in the Sims, and then I'll explain it. And so here in the Sims, you see that when a blue line crosses a green line, you get a cyan color, and when the red crosses the blue, you get a magenta color, and when the red crosses the green, you get a yellow color. And so this is quite simply light theory. This is how light mixes. And so when you have a red LED and a green LED and a blue LED, when you mix those colors, you can get other colors. And so green and red make yellow. Okay, green and blue make cyan, and then blue and red make magenta color when the paths cross. So this is, my simulation is doing this very accurately. This is quite simply color mixing, not unlike color mixing that a painter would do, but the color mixing for paints is different than the color mixing for light. Okay, colors mix, this is RGB, red, green, blue. When you combine red, green, and blue, you get white. Okay, so when the lines cross, you have light from one LED and light from the other LED in this region here, in a cross region. Okay, so you have two light sources contributing, reflecting off the nanoparticles and entering your eye, contributing to what you see. So you see, or the camera sees, these different colors when the lines cross. And of course you see a similar thing in the Ferrocell, and that's what That's what Tim was getting at. He wants to hear my explanation of why we produce a new color when two different colored paths intersect. This is traditional light theory. Okay, this is how light mixes colors, and you see it in quite nicely in our simulation, and you see it in the actual Ferrocell. Okay, so I think this quite nicely. Where is that shown in your Sims? Of course, this is shown in the Sims. This, sort of, this is the way the simulation works. This is not a wireframe. Okay, this is not a wireframe 3D, some 3D model. This is actually a projection. This is a projection, as I think I said earlier. The light, this is a picture of what the camera sees, what the eye sees. This is a picture of what the camera sees, what the eye sees. This is a simulation of what the camera would see and what the eye would see. This is not going on in the Ferrocell. This is not going on in the Ferrocell. I mean, it is, the light is exiting the light source, entering the thin region between, entering the Ferrocell, reflecting off the nanoparticles, and entering your eye. Okay, so this is not even, this is not a wireframe model any more than the Ferrocell is a wireframe model. Okay, this is a simulation. It is a probability distribution. This is what is the probability of seeing a light reflection from your perspective, from the observer's perspective. What are the chances of them seeing such and such a color of light? And so this is the simulation is a very good prediction of what we actually see in the actual Ferrocell. So the final comment I want to deal with here is this one that Tim sent me. He said, "I would be forever indebted to you if you can model a 3D image from a 10 micron thin film." So I'm not 100% sure what he means by that, but I have a feeling what he means is the 3D effect that you see when you look at a Ferrocell in real life. And so when you have the Ferrocell in your hand and you're looking at it in real life, okay, you see that the patterns change in real time. But you also see a 3D effect. And so you can almost see it here, but it just doesn't do it justice seeing it on film. Okay, when you look at the Ferrocell in real life with your eyes, it looks 3D, it looks holographic, it looks like it's got a depth of field. And so I know Tim was talking a lot about depth of field, and so it looks like it has a depth of field, and it's really cool. It's a really neat effect. Okay, watching it on film here doesn't do it justice. You don't get that 3D effect that you get in real life. And so here, what I'm going to do is I'm just going to stop this in different locations. So when it's not moving, no matter which view I pick, it doesn't look 3D. Not like it does in real life. Okay, not like it does in real life. In real life, it looks like there's a depth of field. It looks deep, like super deep. And so, and I know Ken Wheeler talked about it, and I know Ken Wheeler said many times, it just doesn't look the same on camera. It just doesn't look the same on camera. It doesn't look as 3D. It doesn't look 3D at all. And so there's a simple explanation for that, and this is not something you can simulate because there is no 3D. Right? So I cannot generate a 3D image from something that's not 3D. It only looks 3D. So why does it look 3D? Why does it look 3D? And why does it look 3D in real life and it doesn't look 3D, when you film it? And so the explanation is actually quite simple. It's because in real life, most people have two eyes. Okay, so in real life, you are generally looking at the Ferrocell with two eyes. And so this is an optical illusion. This is an effect because there's distance between your two eyes, and this is, a technique that's used to, to make things look 3D, okay, stereographic photography, that sort of thing. And so I could do this. I could do stereoscopic photography and reproduce the 3D effect. It is not a 3D image. You cannot create a 3D model from it, but I am quite sure that I could generate the 3D effect using the stereoscopic approach. But here's the thing. Here's what's really interesting. So in real life, if anyone out there has a Ferrocell and have seen this holographic 3D effect, what I want you to do is take out your Ferrocell, do what I'm doing here, and then I want you to shut one eye. Close one of your eyes and look at the Ferrocell, and then, it might kind of sort of look 3D, but then I want you to open both eyes. When you open both eyes, what happens is it looks 3D again. And then when you close one eye, it doesn't look 3D, or at least it doesn't look as 3D. Your brain might convince you that it looks 3D, but then when you open both eyes again, you will see that it looks really 3D. And you will find that it only looks really 3D, like holographic 3D with a depth of field, when you open both eyes. And so, this effect, this 3D effect that Tim is talking about, is an optical illusion. It's something that I definitely probably could simulate using stereographic techniques. But I don't really think that there's much value in doing that. I know 100% for sure that this is just an optical illusion, that there's no sort of new physics in this in those lines. This illusion, it's an optical illusion. It might look 3D, sort of kind of 3D, but it is just an optical illusion. And so it doesn't really have any sort of new physics value other than the fact that it looks really cool. And it really does look cool. And I highly recommend anyone that, has a Ferrocell or wants to get one, that you have a look. And, this is probably one of the more interesting aspects of the Ferrocell, is this optical illusion 3D effect. So one of Tim's final messages to me were, if you really want to demystify the cell like you advertise, then dig deeper and reveal the mechanisms responsible for all the other phenomenon that's happening. And so I'm sure all the other phenomenon, what he's talking about are the colors that appear when two lines cross, the extra colors, which are easily explained using light theory and color mixing. And the other mysterious phenomenon is the 3D optical illusion that is happening because in real life, we are looking at the Ferrocell with two eyes, which creates a 3D effect, which is really just an optical illusion. And so I'm going to summarize here. So again, Tim said, if you really want to demystify the cell, then dig deeper and reveal all the mechanisms responsible for what's happening in the Ferrocell, is really what he means there. And so the curved lines are caused by specular reflection, or just reflection, reflection off the nanoparticles that are aligning with the magnetic field, and the light is reflecting, coming from the light source and reflecting off the nanoparticles, the needle-like shapes that are forming when the magnet is in place, and the light is reflecting to your eyes. And so this slight fuzziness of the lines is caused by scattering. Scattering doesn't cause the light to go in this pattern. Specular reflection causes the light to go in this pattern. And scattering maybe makes the lines fuzzy, although I don't think there's a lot of scattering going on in this particular Ferrocell because the lines are very thin. The different colors that appear when the lights cross is simple light theory, and it's just color mixing. This is how different colors of light mix. And then the 3D effect that Tim wanted me to address is an optical illusion based on the fact that, and it only works when you open up both eyes. Okay, and so I think I've addressed all the issues that Tim was trying to get me to address, and so I just have one question for Tim, and that question is,